Hey there! The last video talked about solid and liquid rockets, the two main methods of rocket propulsion. But those two aren't the only methods of rocket propulsion, and that's what this video is about. We're going to be diving into the three other methods: hybrid engines, ion propulsion, and nuclear thermal propulsion. This is the third video in a three-part series on the basics of rocket propulsion, so if you haven't watched the previous videos, you can click here to watch them. As always, here are the timestamps for the various sections of this video, so feel free to skip ahead. Well, let's get spacey. Let's start off with hybrid engines. Just like hybrid vehicles, which combine petrol or diesel engines with electric motors, hybrid engines also use a mix of two of the previously covered methods of rocket propulsion, which are solid and liquid rockets. This diagram here shows the basic structure of a hybrid engine. Starting at the top here, we have the oxidizer, stored in either a gaseous form or a liquid form, based on the engine's size. This oxidizer flows through pipes, which takes it to the combustion chamber here, and this is done using valves or pumps, which is also dependent on the size of the engine. Now you may be wondering where the fuel part of rocket propulsion is in the system. The answer lies in the combustion chamber, where we have solid rocket fuel. There is also a hole through the middle, which allows the oxidizer to come through and burn with the solid fuel. Finally, we have a standard converging-diverging nozzle, which was discussed in the last video. So that's hybrid rockets. They're not very common in rockets or spacecrafts right now, but look to become more widely used in the future, especially for microsatellite maneuvering and lunar landers. Moving on to ion propulsion, let's look at how they work. The propellant they use, again, varies, and in many cases, an inert gas like xenon is used. The xenon is then put in a discharge chamber, where the neutral xenon atoms are made to collide with electrons, which in turn takes out even more electrons from the xenon atom, turning it into positively charged ions. The electrons here stay behind to do more of what just happened with other xenon atoms. This process is called ionization. The positive ions are then taken out using a grid at the end of the chamber. Passing through this grid, the positive ions are electromagnetically accelerated, which helps move the ions much faster. This process is repeated over and over at a large scale, with many more atoms and ions, which generates much more thrust. As you see, it is very different to all the other conventional methods of propulsion, which involve a fuel and an oxidizer. Due to some technical limitations, these chemical-based systems can only reach about 40,000 miles per hour, which is a lot, but not so great compared to what an ion thruster could produce, which is about 100,000 miles per hour and maybe even greater. Now, all this sounds good, but why aren't they being used? This is because current technology only allows these engines to produce low thrust in a given amount of time, which makes it unsuitable for large rockets. Many orbiting spacecrafts, however, use ion propulsion, since they don't need to get anywhere quickly and would prefer efficiency over getting to where it wants to be. The third and final method is nuclear thermal propulsion, or NTP. It is a much faster means of propulsion and can help cover vast distances, like that between Earth and Mars, in very little time. It uses the principle of nuclear fission to power spacecrafts and rockets. Development and testing on nuclear rockets began way back in the 1960s, even before the famous Apollo program. However, after the signing of the Partial Test Ban Treaty of 1963, which prohibited all nuclear detonations for political and safety reasons, the development stopped and was not resumed until the 20th century. Nuclear engines use propellant, like liquid hydrogen, stored here, and a nuclear reactor which splits uranium atoms to generate heat. This heat is then used to convert this hydrogen into a gas and pushes it out at tremendous speeds out of the engine nozzle. If researched and developed even further, NCP can help propel humanity further into space and explore worlds much farther than currently possible. So that's hybrid engines, ion propulsion, and nuclear thermal propulsion. They are lesser used methods of rocket propulsion with great potential. With this video, we are done with the Basics of Rocket Propulsion series. I hope you found this video interesting and learned something new. Comment under the video with any feedback or questions, or just like and subscribe if you like this content. And until next time, stay spacey.